Good morning, Year 12. How's it going, guys? All right, so today's lesson, big start, moving on to A-level bonding. Right, we're going to be starting off with Ionic. We've done a little bit of groundwork on this already. You guys have sat a GCSE, a short GCSE assessment, just to look at kind of your base understanding and your base knowledge of bonding from an Ionic perspective. You all did really well. I was really pleased with that, but there's still a small amount of variability. I am going to build bonding up all the way from scratch. It's going to be a quick pace. So beneficial if you watch the YouTube videos back again, will probably be very useful for you. Let's crack on, shall we? So I'm going to share my screen. Share my screen. Boom. There we go. I'm now going to actually switch off my camera. I don't think it makes any difference in reality. Okay, right, today's lesson. Let's zoom in, shall we, folks? Right, today's lesson, we are doing AS Bonding Lesson 1. It's going to be quite a long series. I'll do my best to try and get them done as in as shorter space as possible, but I don't like to rush bonding. This is the most important topic I can ever teach you in the history of chemistry. This will be your foundations for everything. Could I just have a quick ask everyone in the classroom just quickly to pop up on the chat, please, and say hello, just so I know that you've got it and you're there and that you can hear me okay. That would be great. Okay, 4 learning objectives today, guys. So a tough lesson. Yeah, 4 learning objectives. I tend to like to try to aim for 3, but I'm going to be focusing on 4 today. Hi, Yehern, great to see you. Right, okay, so at least I know everything's running and everything's okay. Can hear you, sir. Hello, great job. Okay, so number 1, define electronegativity. So this is a brand new word for you guys. Most of you will not have heard it at all. Some of you might have heard it in lessons through either through, I don't know, family members or or other lessons where it just gets briefly mentioned, or anyone who's done the extra reading at GCSE may have come across it. But this is new. And know the periodic table and how it relates. That's actually quite important, that. How to use the periodic table to find these values. Yeah, that's where that's going. So not no table EN numbers, electronegativity numbers. Yeah. Number 2, understand the difference between electronegativity decides bonding type. Yeah, so we know that there's going to be a discrepancy between these values, which means that actually leads to the type of bonding that we see. Number 3, know your oddities. Now, this is an ionic specific setting. Yeah, and then draw and describe the structure of ionic compounds. So that last one is going to be the extension from GCSE, but all of this is now new to you guys. There are going to be all the way through this are new points here that we're picking up. Okay, so the first thing I'd like to do is I'd like to do Ionic GCSE, and I want to do facts. I feel like it's always nice. I always say that I like to try and teach bonding from ground up every time I go back to it. So kind of laying down important facts that you picked up at GCSE are really, really handy in being able to develop an A-level understanding. So the first fact, number 1, we know that ionic compounds contain ions. I know that seems odd, doesn't it? Ionic compounds contain ions. So for example, sodium chloride, solid, yeah, what we realize that actually looks like is Na plus, yeah, and Cl minus. Notice they are not overlapping. Yeah, and this leads us to fact number 2. Fact number 2. Right, and this is an extension. This is a GCSE. You were allowed to say ionic bonds. This is now completely banned. You are never, ever allowed to say the word ionic bond, and I am not putting into your notes. Yeah, the reason being is it's banned, and I've got to delete that. Delete it from your repertoire. There is no actual bond between ions. What there is, number 2, between ions, between oppositely charged ions. This is all GCSE. Oppositely charged ions is the, notice my changing color, please do the same, is the and you've got to learn this, folks, electrostatic attraction. So we know that opposite charges attract. It's one of the most important fundamental facts in chemistry that is so vital. That force, by the way, is the force that basically chemists spent the entire time using. Physicists can use a couple of other forces, but we don't use any others. That's the only force we talk about. Next, number 3. Fact number 3. How could we prove this? There is a test. Test for ionic compounds. This may be new to you. Yeah, if you had me at GCSE, it is not new. Test for ionic compounds. ... Yeah. Add solid to, oh no, it's not. I tell a lie. Melt, sorry. Melt solid, melt solid compound or substance. I prefer substance because you don't know if it's a test, you don't know what it is. Melt solid substance and test to see if liquid conducts electricity. Electricity. There we go. So that's actually really, really important. That is a basic test for if a substance was ionic. Lots of students would argue that you'd be able to do a whole load of other tests to be able to prove if something is ionic. And to a certain extent, that statement is true. But unfortunately, like people often say, well, hang on a minute, I could add it to water and test it for the ions. And I'm like, well, actually, that's not entirely true. The reason being is you could have something like hydrochloric acid. I know it's a gas, but for just argument's sake. Yeah, you could take solid, solid hydrochloric acid, which would be very low temperatures, but a solid. You could add it to water, yeah, and it would conduct electricity because it would be forming ions as a result of being in water. That doesn't mean it's ionic, though, because it wasn't. It was covalent. It means it is ionizing in water. So the point I'm trying to make is I don't want you to make a whole load of notes on this. And in fact, the reason why I'm talking this through, because and not writing the notes is because I want you to learn that fact. The test for ionic compounds is to melt a solid and test to see if the liquid conducts electricity. That is the only genuine proof of ionic compounds. Yeah, okay. Next thing. Okay, what else do we have from GCSE? Okay, the next thing is all ionic compounds have, I'm ahead of myself, have high melting points. I'll be good. I won't write MPT. I'll be good. Have high melting points. Therefore, are solids at room temperature. S at STP. It's nice to see the train station symbol reappearing across topics. Do we say molten instead of liquid? The word molten means hot liquid, Anch, is what it means. And if you're going to, you're right, to see if, you would say molten liquid. Or when the substance is molten, isn't that weird? Yeah, see if, yeah, hot liquid, molten liquid, sure, can. Wouldn't make any difference in that particular scenario, that, Ange. Yeah, but molten means hot liquid. That's what it means. We've seen this, of course. This has made a reappearance. We have seen that in both atomic structure. Yeah, we've seen that in atomic structure. We have also seen it, atomic structure. You guys have also seen it in kinetics and equilibrium. It was seeing it everywhere. Yep, seeing it all over the place. So it's nice to be able to remind ourselves, standard temperature and pressure, 298 Kelvin. Yeah, we can just add that on here, can't we? 298 Kelvin. And 100 kilopascals. I don't actually like quoting kilopascals because in PV equals nRT, you have to quote it in pascals. I prefer actually just to put it in pascals. But anyway, just something to consider. So, next one. Fact number 5. Fact number 5. Right. And this is the one which I'm now going to star. Yeah. Ionic bonding occurs when ... Okay, this one, guys, is really important. We're going to say when metal, silver and shiny. Oh dear, that's too big. Let's make it a bit smaller. Metal, nope, don't like it. Don't like it. When metal bonds, reacts, it's better. Bonds, reacts, It's the same thing in this case. Reacts / bonds to non-metal. And I can put, I can see what I'm doing here. Non-metal, I'll put it in orange, why not? Non-metal. Cool, right, and there is the electrostatic attraction, elec-stat. Nice, okay. So now I need to now put this one in a big red sparkly box. The reason being is this one is now going to evolve. Now guys, this is still a great rule. This applies about 85% of the time, but it's not 100% of the time. What that means is this is therefore going to have to be deleted and replaced by the A-level version. Yeah, we are going to replace this, with A-level version. So can I just point out, however, this is not something I want you to actually delete because it's super handy. If someone asked me, cesium chloride, and I'd probably go, probably ionic, probably, but it depends. But I'm going to guess ionic. If I didn't have anything in front of me, if I hear a metal and a non-metal, I'm going to assume it's ionic. Yeah, I'm not going to start running numbers on it to prove it. I can, but like I said, it's going to need to be replaced. Right, number 6, diagram. So the diagram at GCSE there are 2 diagrams at GCSE. Diagrams, and these still apply at A level. So diagrams. Number 1, we have diagram A, and this is the reaction. The reaction diagram, and what the reaction diagram shows is it shows the metal, something like sodium, yeah, giving its electron over to something like chlorine. Yeah, this is still done at A level. Yeah, there we go. There's the reaction. And then this diagram is so important because it allows us then, that's the reaction. Yeah, the transfer of electrons. The transfer of electrons. We can now describe this thanks to GCSE. And I know I'm going to be making all of these cross-topic links now. Yeah, if we look at that as a transfer of electrons, we can look at it in terms of redox. Yeah, we know oil rig from GCSE. Yeah, oxidation is the loss of electrons. Reduction is the gain of electrons. So what you can realize is that the sodium is going through oxidation since it is losing electrons, losing 1 electron, got to quantify now. Yeah, whereas chlorine is going through reduction because reduction is the gain, because it is gaining 1 electron. So these diagrams are so important for the understanding of what's happening in chemistry. We deal with electron transfer the majority of chemistry, so this is important. Right, the next one, B. So the next diagram, that was the reaction. The next one is the ion diagram. Once again, the ion diagram still exists. So the ion diagram is turning these symbols yeah, turning these symbols into a pictorial representation of them. So there's actually a couple of different versions of these. There is the simple version where you're only showing the outer shell only. And this one, of course, is the one that everyone prefers because sodium is awesome. It just loses its outer shell, yeah. And chlorine, of course, gains the electron. So that one's a bit more complicated. That one you have to show it as these are called dot and cross Lewis diagrams, by the way. And there we go. Here's the Lewis diagram. That's showing the outer shell only. There are other ones which are slightly more complex when they want you to show all of them. When they do that, they usually tend to make you draw the before and after. If I write that one there, in fact, if I just zoom in a bit, if I write that one in red, what I can then do is show you the fact that the red one requires you to show sodium beforehand. Yeah, so the sodium beforehand having one, 2, 3 shells. Yeah, 2 electrons in that shell. And then 6, you realize you're going back to GCSE dot and cross 2882. It's not disappeared. You're still going to need it. And then showing chlorine with its 7. Yeah, chlorine with its 3 shells. Yeah, in dots this case. Like I said, you don't bother with the subshell idea. We don't deal with it with Lewis diagrams. Yeah, and then, so now, of course, I can now show, the transfer, of course, is just that. And then realizing that the full detail with all shells, what you realize is that sodium has lost a shell. Yeah, it becomes smaller. Yeah, it's now only got, I really want to just make an effort to make them similar sizes. It's now shrunk in size. Not only has it shrunk because it's lost a shell, but it has also shrunk because it's +1. Yeah, there we go. And then the chlorine one, of course, gets bigger. First shell, second shell, third shell, and it swells in size. Then you have, doesn't matter that I put it on the corner. Doesn't matter. Got a bit mad there. Putting them on all over the place. There we go. All shells being shown. But these diagrams are very common. So this is all GCSE. Nothing really new at A-level at this point. It's nice to realize that this is still GCSE, even though it seems a bit more complicated when you put it into the redox setting. But nice to see the connection. Yeah, we're now realizing that this rule that we've become so dependent on is about to evolve. But there are these lovely key points here. I will also mention, so at this point, there is technically a third diagram of the lattice structure. I'll add, did I say 2? I'll put diagrams. So this is C, diagram number C, or letter C. Yeah, so this one again is a GCSE that's about to evolve. So we've got a sodium ion, followed by a chloride ion, followed by a sodium ion, followed by a chloride ion, followed by a sodium ion, followed by a chloride ion. Notice there is no overlap. Yeah, these are not overlapping. If you make that mistake, you lose marks. So this diagram is what is described as a simple representation. A simple representation of the ionic, and this is a key word which I'm about to change my color for, lattice. Yeah, we know that ionic compounds are cool because in fact they're giant structures. Once again, this diagram is going to evolve. These ones kind of remain exactly the same, but they're going to make them slightly more complicated with more people. The reaction one will remain very similar, but again, they'll just make it a bit more complicated with different ions. But this one will evolve. So I can circle this one as, can box this one off as well and say this picture is now going to evolve at A-level as well. This now needs a more complex diagram. We now need to evolve this into the 3D diagram for A-level. 3D diagram for A-level, which is nice to demonstrate our understanding that the lattice is not 2D but 3D. I like it. Okay. Other things from, I think that's all the diagrams that I really want to cover from a GCSE perspective. The next fact, that was number 6. Let's go for fact number 7. Fact number 7 is properties. Yeah, we have these properties brought down from GCSE. Properties of ionic compounds. And these really do need to be clamped down. Now, the way that I teach this at GCSE is I just simply say, for every bonding type, you should have an example. And that example should just be very clear in your mind. You can picture it and you can manipulate it. There's this idea of being able to develop your spatial awareness and your imagination to be able to run what Einstein used to call thought experiments. So the example, of course, I have in my head for ionic is glass. Yeah, we all know. Oh, look at that. Oh, nice picture. All right, I'm going to come to that later. So glass. I just want a picture of glass. Images. It's going to give me a film. Yeah, we all know. We all know glass well. We use it on a regular basis. This is why it's such a great example of an ionic compound to latch onto. You know for a fact that it has a crazy high melting point. You know, we put hot coffee into these things. We put it into the microwave. We put it into an oven, and it smiles back at us. Yeah. So the example here I always focus on is glass. I'm going to increase the size on this. Oh, blimey. Okay. Changed pendant tie, so it was already set up. Glass. And we can pick up key properties of ionic compounds. So we have got high melting point, high MPT, and BPT. You're not allowed to do that in your exam, by the way. They won't know what that is. Yeah, but it's good to have. Next thing, they are brittle. If you drop glass on the floor, it will smash. Yeah, you're not going to bend it. The opposite of brittle is malleable, which is if I can bend it and its shape remain intact. So it's brittle. The next ones, of course, and these actually I'm going to star as the most important. Yeah, they conduct electricity when molten. There is the test. Molten or in solution. I'm going to put in solution brackets AQ. I like it. And we'll need to be able to explain those particular things. They are also inert. Now, I don't tend to like talking about inertness because the inert means unreactive, but that doesn't mean that they're not toxic. There is a difference between being inert, which is unreactive, and toxic. Those are not the same things, but they are inert. The reason being is they've swapped electrons, they've gained, they've swapped electrons between the atoms to form ions. Those ions now have noble gas configurations. So why would they want to do anything else? Yeah, unless you start adding things that are more reactive to them, they tend to be relatively inert. But I'm actually going to tell you not to bother. We can just put a cross through that one and say, these two are the ones I need you to know. Yeah, those are the top answers. Brittle does make an appearance every now and again. They'll say a student that has an ionic solid with a high melting point and conducts electricity when molten or in solution. Give a third property. That does happen, and brittle would be your choice. Yeah. Just quickly, just to reaffirm something really cool about glass. Yeah. So I wanted desperately to build this in school. Unfortunately, though, I was banned. Was not allowed to build this one. So this is glass conducting, MIT. So MIT do this. And this short video, if you had me for GCSE, you'll have seen this before. So MIT set up a very, very simple process, very simple little demonstration here. So they've got a simple circuit plugged into the mains, and they've got these copper tubes, and you can see the wires on either side of the copper tubes. And when he puts his metallic screwdriver and joins the two copper tubes together, the circuit's completed and the light bulb comes on. Well, at the top is glass. And this is just the top of a pipette, by the way. So this is just standard pipette glass. And at the minute, you can see it's not conducting. Yeah, so he's now going to heat it up. Now, at the beginning, no change at all. He's got to get this to the point where it's molten, when it becomes liquid, when the ions become free to move. And now you can see that it's conducting electricity. Glass is definitely ionic. So it's quite nice that to be able to see, and as I said, I really want to be able to demonstrate that in class. That is super cool. And then as soon as the liquid breaks apart, the conductivity stops. It's just really nice. I just think it's beautiful. Such a wonderful demonstration. Really, really is. As I said, maybe one day I'll build one at home just for fun. Anyway, so we've picked up properties of our ionics. Now, the next thing I want to do, fact number 8. This isn't so much of a fact, so much as sorry about the knocking, by the way, guys. They're doing work, flat nearby. Number 8 is I just quite like to elaborate on what kind of questions you remember from GCSE, and one in particular. Yeah. So questioning, question types at GCSE include explain, explain, ... high melting point, high MPT, explain, conductivity, create formulae. You realize formulae is part of Ionic. Create formulae. Create a formula, if you like. And that's about it really for now. I'll link it to chemical tests another time, but those are the ones. Whereas A-level, this is going to become slightly more challenging, but these still stand. And in fact, one of the nice things about GCSE is you can use the same method for explaining the GCSE as you do in A-level. Okay, so let's go back to my learning objectives. Right, let's see how quickly I can rustle through this. So what I'm now going to do is I'm now going to step in and say A-level. Right. A-level Ionic. Okay, so first thing I need to do is break the metal non-metal rule. So we realize that ionic compounds are formed when a reaction between A and B, it doesn't matter what they are, that's the point. Reaction between A and B involves exchange of electrons. So, e.g., let's say that A is going to give B its electron, and as a result of this, I'm just going to put some electrons on just for fun and games. I'm actually going to show a better arrow, just not that it makes any difference. And that will result in A becoming positive. A becomes positive because it's lost an electron, and B now becomes negative and gets bigger. A gets smaller, B gets bigger. Love linking it to size of ions. And B becomes negative because it's gained an electron. But the point of this, the bit of underlining, is transfer. Is formal reaction involves exchange of electrons. So in order to exchange electrons, we used to say that metals lose. And are there any more facts? Not at the minute, Ange. If any more come into my mind, I'll add them. But no. Okay, so we've been saying for ages, for the whole of GCSE, we've been saying metals lose, and non-metals gain. That's what we've been saying. Non-metals gain. That's what we've been saying. But the problem is that this actually isn't entirely, it's not always true. So the reason is we need to look at how an atom holds on to its electrons. And the way we do this, we need to measure the strength of an atom to hold on to its electrons. So how do we do that? And we do this through electronegativity. Electronegativity. Right, and the definition is, I'm sorry for this, guys, I'll explain it in a minute. The power, or strength, if you prefer, the power of an atom to attract a shared pair of electrons, the power of an atom to attract a shared pair of electrons in a covalent bond, towards itself. Right, that means absolutely nothing. Isn't that amazing? I'm trying not to make my writing get too big. I need to try and keep some consistency of it. Right, so what does this mean? What this means is I often like mentioning this idea of the alternative word of strength. Yeah, it's totally allowed, absolutely fine. In fact, some teachers prefer it. The reason being is strength allows students to imagine this like you would measure your strength. So let's say I wanted to measure Ansh's strength. I want to measure Ansh's strength. Now, what I'm going to do, there's Ansh. His hair's a bit all over the place these days. Ansh. That's so mean. I'm so sorry, Ansh. I love your hair. It's great. So we've got, God, he's going to hate me for that. I want to measure Ansh's strength. There you go. How's that look? We want to measure Ansh's strength. Now, the problem with measuring Ansh's strength is I could just simply ask him, Ansh, how strong are you? And what he would say is, I'm all right. Yeah, I'm pretty strong. But we can't quantify it. We cannot give it a numerical value. The reason being is it would become objective. It is, he's deciding on what it is. Sir, my hair is a bit longer than that. Yeah, you're right. It is, Ansh. It is a bit longer than that. You're absolutely right. You're right. There you go. Is that better? Is that better? So in order to measure Ansh's strength, what I'm going to need to do is pitch him against somebody else. I don't know if this is going to work. I don't know if this is going to work. It's not going to work. I want to clone it. Copy. That didn't work at all. Oh dear, I've ruined my notes. Delete. How do I delete this? With no keyboard. Delete. There we go. I want to try and I can alternatively copy, paste, and then flip, rotate. No, order. I want to flip it. Oh no, you're not going to let me flip it. It's not going to let me. Oh, it's not going to let me flip it. Draw. Oh no, you mean thing. I'm so close. I just need to flip you to the right. Order, group, rotation, flip, horizontal. Way! Yes! Look at that. So what we need now to do is we need to pitch Ansh against someone else. Yeah? Let's pitch him against Louis. Oh, I don't want to delete his face. Let's pitch him against Louis. I can't remember for the life of me what Louis' hair looks like. Yeah? So we've got Ansh versus Louis. Yeah. So we're going to pitch them together and they're now going to arm wrestle. Now this will allow me to determine, yeah, that's about right. Yeah. So what this can now do is I can now say which one of those two is going to be stronger, which one is going to have the greater strength. Now, in terms of atoms attracting electrons, what we needed to do is we needed to compare an atom's strength. So let's compare atoms A and B. We're going to put atom A and B, and we're going to put them in a bond. And what we're going to do is you can see the electrons in that bond. Yeah, these are the shared electrons. The shared electrons. Now, what we can now do is tell whether or not Louis wins. What we can now do is realize that the electrons are not going to be in the middle. What's going to happen is B has a greater power. Yeah. What's happened is B has pulled the electrons towards itself, and A has lost. So what we can now determine from that is that A, I'm going to have partial charges. I'm not going to do that today. It's covalent. But what we can now say is that this one has a higher electronegativity. You can't electronegativity. You can't measure somebody's strength outside of a bond. Yeah? So the strength of an atom to attract a shared pair of electrons in a covalent bond towards itself. Okay. So now that we've figured out how we're measuring an atom's strength, how much they want electrons, which is quite literally what we're doing, yeah, what we now need to realize is who's the empress? Who is the strongest of them all? Can we predict this? So let's consider this from a periodic table standpoint. If we want to attract electrons, we want to for an atom, for atom A to attract an electron. In order to do that, what we want is loads of protons. Well, hang on a minute. Loads of protons is going to be this side of the table, because as you move across, you gain protons. Winner. So, okay, first thing is lots of protons. But the next thing is you need as few shells as possible. You want it to be as close to the nucleus as possible. So the question is, who's going to have the highest electronegativity? Who's going to be the king of electronegativity? And there's only one answer. I wonder if anyone can predict this. Would anyone like to have a guess at who it would be on my table? Just on the chat. I know that the lesson's coming to an end. I've got nowhere near what I wanted to do in my learning objectives. Outstanding. Well done, Yi Hearn. It's her. Oh, it's her. Fluorine. Holy moly. Fluorine is the most reactive element in the known universe. She can react with noble gases. She is that insane. She is that powerful. She can pull electrons, not off, but she can certainly share electrons with noble gases because she is that crazy. Yep, she has got 9 protons and only 2 shells, and she is tiny, really, really small. Yep, so now at this point, I can now mention the Pauling scale of electronegativity. I wonder if I can find you a picture of Pauling. Sorry. The Pauling scale of electronegativity. I'm trying to remember what the guy's name was. It's annoying. Doesn't matter. But by the way, I usually remember the ink because I always remember it's like the pulling scale. Do you see what I'm doing there? Yeah. This is the Pauling scale of electronegativity. Pauling, like pulling, because it's pulling. B is pull. I'll stop. So the Pauling decided that he was going to create the scale, look at which atoms are the strongest, and number them. Now, you only need to know a few of these, but what you need to know is a section from my table. Yeah, what I would recommend doing is learning the 7 diatomics. They're really, really useful. Yeah, so if we do the 7 diatomics, so hydrogen, so this is the Pauling scale, hydrogen. This has a Pauling scale, so an electronegativity value, an En value of 2.1. Is that correct? No, 2.2. 2.2, I believe. 2.2. Next, okay, carbon. Carbon, 2.1, I believe. Oh, I'm going to get those two the wrong way around. I always do. It makes no difference. They're essentially the same. It's an important thing to know. Carbon, oxygen, hang on. Lithium. Oh, why have I gone mad? Lithium, beryllium, boron, carbon, nitrogen. So nitrogen. Oh, should just do it like this. Yeah, nitrogen, oxygen, fluorine. Yeah, so fluorine is 4, by the way. That's the highest one. Oxygen, 3.5. Nitrogen, 3. 3.0. Carbon, it's higher. It's about, okay, so that's going to correct me. It's about 2.2, give or take. You can actually call it 2.5. It is allowed. And that's going to be about 2.1, I believe. We'll check it in a sec. So knowing these guys is important. Now, the reason why I like teaching the 7, the reason why I like teaching the 7 is I teach a pattern. Yeah, I teach a pattern. Bromine, iodine. So the chlorine is 3.5, bromine is 3. Now, these numbers aren't accurate. There's slight differences, but it works. It's actually, she's one angry woman. So just to show you how I've just done that, I've just remembered the number 4. I'm going to make my pen a bit thicker. Yeah, all I have remembered is the number 4 for fluorine. And then I remember every step I take away from fluorine, I drop by 0.5. So 3.5, 3, 2.5. That works. Yeah, and then 2.2 up there for hydrogen. Makes the difference 0.3. There's a reason for that. And then 3.5, 3, and 2.5. It's a really useful little trick. Now, you can't move diagonally, just warn you that. If you were going to go to sulfur, you'd have to make a double bounce. Yes, that would be 3. It's just nice to talk about that. But the great thing is, all you have to learn is one person. Just learn fluorine. Oh my goodness, she is important. Fluorine is an amazing element to know about. She's so useful. Yeah, fluorine. Love fluorine. Yeah, fluorine. Symbol F. Highest electronegativity. En value of 4.0. Yeah. And also the most reactive in the known universe. It gives you all the trends in my table. Such a useful element. And I can nearly call it an elephant. Such an important element to know. So handy. Right, so I know that my lesson's gone on slightly longer than I anticipated. I just quickly want to now fix my definition. Yeah, we'll pick up the others after. Continue that next lesson. My writing's getting bigger and bigger every time. So, a new definition for when ionic occurs, right? And this will be the end of my lesson. So, in fact, I can go back to the very beginning because I took it from the table. Right, and here it goes. There it is. There it is. So, I'm actually going to give you the actual fact because this is what you need to quote in an exam. Question, when ionic, I'll give you real ones in your homework. Yeah, when ionic. Answer. When there is a big difference in electronegativity. That's when it occurs. When there's a big difference. Yeah. So if it's similar, yeah, so we can then pick up the next one. When covalent. When they're similar. Answer. When electronegativity, negativity is similar. And at this point, people will say, well, how big does it need to be? And there is the answer. Yeah, I'm going to end on that picture today on my lesson. Yeah, a difference of 1.8 or higher. I'm going to end there today. What I'm going to do is I'm going to send you out your homework on the classroom. It's an exercise where you actually apply that rule. So I'm going to leave that there today. I will then go through that homework then on the YouTube video as well. Start cam. Okay, guys, I'm going to leave you guys be. I hope you found it useful. We've summed up ionic bonding for GCSE, come up with some clear facts. I need you to assimilate those, learn them off by heart. It's really important. They're great value. Yeah, and then we're starting the process of developing this understanding of where ionic's coming from, and we'll continue that next lesson. I'll see you guys very soon.